Everyone. I'm Eric Nalisnick. I'm also at the University of Amsterdam in the same lab as Willem. And today I'll be talking about towards anytime computation in deep architectures. I'm actually going to. Oh, there we go. I'm actually going to talk mostly about supervised learning. So yeah, sorry, organizers for going off script a bit. But the idea came to us, with James Allingham and myself. The idea came to us from reading the classic Jeff Hinton paper on cognitive experts from 1999. And if you look in this paper, has this example of great generation results. He could actually generate clustered points along this grid. So on one hand, it's great that we've come so far. On the other hand, I still see this as a toy task in some papers, so maybe we haven't come that far. But the setting I'm going to be interested in is these early exit architectures. So the idea is that we have our input features come in, they go through a series of hidden units, just like any neural network, but they can choose to we can either choose to compute another hidden unit or to exit and compute an output distribution. And so that's why the early exit name comes from. And the goal is, can we say anything about how this distribution would relate to our final distribution? That is, if we short circuit the computation at any time, can we get any guarantees with respect to the final model output? And this is motivated by self-driving car examples. Like, so for instance, a car might have to make quick decisions in a city environment, but can think much longer in a rural environment. And also in mobile phones, I think there's something like 25,000 different computational configurations in Android devices. And so when you deploy your model to a phone, you don't know actually how it's going to be limited by the resources. And so you want to know, at least if I can get to the first exit, it'll only get better after that. And so our contribution was we have an ensemble formulation for which model uncertainty is guaranteed to not increase as more members are evaluated or more exits are evaluated. And we do this through two key ideas. We train the early exits as a product of experts, and we force each exit or the expert to have limited support. So first, just to remind you what a product of experts is, it's simply just kind of like a mixture model, but instead of taking a sum over the components, you take a product. And so here we'll be taking the product over these exits right here. But unlike a regular mixture model, you have to normalize. And so you have to integrate over your y variable here. And this is really hard to do back in the day when Jeff Hinton was doing it, and still today, because he was training generative models, and so the integral would be over your full feature space. But here it's just a label, so this integration is easy to do exactly or approximate well with numerical methods. And so here's the core idea of the work, is that if we consider our support space, our conditional distribution y given x, and we evaluate our first expert, our first exit, P1, and it has the support given by the shaded region here, we can look at its intersection with the second expert, or the second exit, P2. And because we have a product of experts, we know that the predictions come from the product over these two distributions can only come from their intersection. And therefore, if we add another exit, we know that it can only come from the intersection still. So we reduced our kind of support space for the predictions from here just to here. And so if I were to add a fourth exit, the predictions can only come from here. So if the distribution perfectly overlapped, it'd stay the same, or it would just continue to cut out from that intersection. And we can use this idea to have the following guarantee. So if y star denotes the mode of the full product of experts, then for any m-size truncated ensemble, we know that the probability of the mode will only go up as we add additional exits. And so here's just an example for anytime regression. So we have an observation at x naught, and usually we put a normal distribution around to make our prediction. But instead we'll put a uniform distribution. So here's P1. Then we have P2, another uniform distribution. And of course, the product is their intersection. So that would be our support for our prediction.
Eric, is this a probability mass or a probability density? Or
this would be a continuous uniform distribution. 3, and that will take the intersection still. So you might say, okay, that's kind of cute, but like training actually uniform distributions to do regression seems really hard, right? Because you can get an infinite likelihood. And so the problem is how to do this in a soft way with gradient descent. And so the idea we had was to use the generalized normal distribution, which is a distribution that interpolates between the uniform and the normal distribution in a soft way through this beta parameter. And so you can start off training by just training the normal distribution and gradually make it more and more uniform as you go along. And so here's some just toy example results for regression, just to show that we can do it. But I'll move on to classification in the interest of time. And so you can set up the same thing for classification, but now you have to use hard one-verse-all classifiers. So you can think of each exit as kind of casting the vote for a label, and the label that gets predicted at the end is the one that receives a vote at every exit.
Sorry, Eric, I missed the points. Why did you switch from normal to uniform?
Because we need this. You could possibly use a truncated normal, but so you have to have some limited support, right? Otherwise, you can kind of change the distribution arbitrarily as you add a new exit. So you need to have that limited support to stop that. So yeah, you could possibly use a truncated normal, but I think you have to make some assumptions about how it's shifted within that truncation region.
What happens if they don't overlap?
So you would get to oh yeah, so your probability goes to 0. Yeah, so that's why you need to do like a very careful scheduling of this beta parameter. But I mean, at worst case though, like at test time when it doesn't, you can just fall back to not evaluating it as a product. We find that works fairly well too. Yeah, so here's some classification results. And I'll just finish up with some food for thought of, as our models grow larger, is it time to revisit things like older ideas like product of experts for other qualities, and such as anytime generative modeling, as I show here, or maybe the broader point is, as our models grow larger and we want to deploy them to more and more different devices, can we have computational knobs that allow us to say, okay, you'll get this quality of generation results with this by tuning this knob a certain way. So thanks. Here's a link to the workshop paper. We'll have a full conference paper hopefully coming soon.